This is lesson 2 of the independent unit on matrices. And today we're going to start using matrices to actually solve some systems, actually do something with matrices. So just, again, a little bit of stuff on notation to start. It says here there's 2 ways in which we can express linear systems using matrices. We're going to look at them both, but we're really only using one of them. But if it comes up at some point, then at least you've seen it once. So one of the ways, if I'm looking at this system, which is obviously 3 planes, is I start by just writing out the coefficients. And that's a matrix all by itself. And in fact, that has a name. It's called the coefficient matrix. And then I do a thing where you write x, y, z, like this. And if you actually think about matrix multiplication, this would be like 2 times x, negative 1 times y, 3 times z, which gives you that first part. And so we set this equal to 4 and 3 and 3. And this is just another way of representing a system using matrices. But that's not the one that we're going to use, but at least you've seen it once, and it is used in linear algebra and other kinds of things. You do that kind of matrix representation. But a little bit more of a simple way, if you're just solving systems, is to use something called an augmented matrix. So this is how we are going to actually solve systems, and this is the one that you really need to know how to do. So we're just going to take a look at a simple system. And this is in 2 space, so this is actually 2 lines in 2 space. And it would be kind of overkill to use matrices, but it's a simple way of sort of introducing the topic. So I'm going to go ahead and write the augmented matrix for this system. How do you write an augmented matrix again?
You're telling me you can't remember? Just use those numbers, and then those are the coefficients go on the left, and then you put a line, and then you...
Oh,
okay.
yeah.
Wait, are we going to edit this?
No, I muted the...
Okay,
It's okay,
all right,
it's okay.
just put it in. So just write another matrix, put the coefficients in, don't put a separate matrix, right? Just draw a line, that'll be like your equal sign, and put the 5 and the 6.
Right, okay, yeah, I got it.
Okay.
Okay, so writing an augmented matrix is easy. You just start with your coefficients, and instead of doing a different matrix, you do a line, which is like the equal sign, and you just finish it like that. This is what we call an augmented matrix, and it's a little bit of a simpler way of representing a linear system. Now, the process that we're actually going to use has a few different names. One of the names is called Gaussian Elimination, or sometimes it's called row reduction. And there's sort of the procedures that we're allowed to do, or the steps that we're allowed to do, kind of fall into 3 categories. So you can either swap 2 rows, and you'll see why this is important later, not really in the first example, but in later examples it'll be more obvious. You can multiply any row by any non-zero number. You certainly can't multiply by 0, and sometimes we want to divide, but usually instead we multiply by fractions. Or you can add any multiple of a row to another row. So those are kind of the 3 basic operations that you can do. Okay, so I'm going to go ahead and start this one again. Same system we were looking at before. And now I'm going to go ahead and solve it. Okay, wait, what do I do again?
Listen, this is so easy. It's elimination. You need either the x coefficients to be the same, or you need the y coefficients to be the same. And then either subtract the 2 rows or add them. Put it on mute and we'll go through this.
Okay, yeah, no, I'll just edit it later. Don't worry.
All right. So I don't know, you can multiply row 2 by 2 so that the first 2 are both 2s, or you can multiply row 1 by 2 so that the second are both, like one of them's a negative 2 and one of them's a 2.
I think I got it. I got it. Okay, so all I'm going to do here is I'm going to have my next matrix, and I'm going to set up the x's so that I can eliminate. And to do that, I'm going to multiply row 2 by 2. Or you can multiply by negative 2 if you want to add, either way. The one difference, or maybe it's kind of the same, but it's a little bit strange getting used to, is we do it like this. So row 2 times 2 is we write it down here to show what we're doing. And so this becomes 2 and 4 and 12. And I haven't touched row 1, so I can just leave it alone. And just like that. And now, I think you can see what we're going to do is we're going to do row 2 minus row 1. So 2 minus 2 is 0. 4 minus negative 1 is 5. And 12 minus 5 is 7. What do I do now?
Did you fill in the
Does this mean there's no solution?
No, it doesn't mean there's no solution. That 5 is in front of a y. That 7 is, that's an equal sign,
yeah,
and
yeah,
that's
yeah,
7. That's like 5y equals 7.
Okay. So obviously, we're done now, and we've got to the end of our matrix solution, and we're actually going to stop here. There is a way to continue, but we're going to stop here. It's just as easy, and I think it's pretty obvious that this means 5y equals 7. And so then I can divide both sides, and I can actually get my value of y, and it works out to 1.4. And I'm going to take this, and I'm going to solve for x, and I'm going to use this version, which is now like 2x minus y equals 5, but I know y, so I get 2x minus y equals 5, and I get 2x equals 6.4. I don't know why I'm working in decimals, but I am, which is 3.2. And that's a pretty simple one. Usually there's a lot more going on, but again, when you're working in 2 space with 2 lines, it's not super interesting, not super exciting, but it gives you a general idea of how these systems work. Let's take a look at one that's a bit more complex and one that we're more interested in. So this is obviously 3 planes in 3 space, and we are going to set it up the same way. So I'm going to start writing out the coefficients. Okay, and I mentioned before that one of the operations you can do is you can swap rows around. So I'm going to show you why you might want to do that. Now, I didn't talk about this before, but actually, your main goal when you're doing this is you're trying to get zeros in all of these positions, because that's what's going to allow you to solve for your z, and then you're also going to be able to you would be able to solve for your y and do the operations. You'll see what I mean. Do the operations that you need in order to get this in the position where we can solve it. So if I want to get these in the bottom left here equal to 0, it looks to me like these ones are lined up nicely to eliminate. So that's what I'm going to start with. But I want them in the bottom corner, so I'm going to take row 2 and put it here. I'm just going to swap it. And this is how we show it when we want to swap rows, which is one of the things that we do a lot of. And I'm going to put row 1 here, which means row 2 has to go here. So that's definitely different from anything you've seen in the past. What's wrong? Row 2, row 2. This one's row 3.
That's row 3, row 1, row 2.
Okay, I'll fix that after. I'll
Just edit that out.
Yeah.
Okay.
Okay, so now I'm going to take row 1 and multiply. You could just subtract, but I'll show you what it looks like multiplying by -1. Oops. So I'm going to do, this is the new row 2, so I'm going to do like negative row 2. And I'm just going to fix all these and leave everything else the same. If you like adding more than you like subtracting, this is a good way to do it. Now, I need this to be 0. So here, I'm going to do my new row 2, which is this one. This row 2 is referring to just the row 2 of the matrix above it, not any other row 2 from the beginning. And I'm going to add that to row 3. And since I put it here, it means I'm putting the answer in this space. So those give you 0. These give you -3. These give you 2. And these give you -4. And I believe I'm leaving everything else alone for now. How am I doing now?
Okay, but like, you're not done.
Okay, right. Okay, so now, next thing I want to do is I want to get rid of that one, and I want to turn this into a 0. So I am going, and I could have, the nice thing about matrices is I could have actually, if I was looking ahead, I could have done that in the same step. Okay, but I didn't see that, so I'm going to do 2 row 2, and I get -2, -2, -2, -8. This one's still 0, -3, 2, -4, and this one's still 2, 3, 1, 9. So all I changed was that one. And now in that same space, I'm going to add row 2 and row 1. So this one's not going to change. This one's not going to change. And I'm going to add these together. So that's 0, which is what I wanted. That's 1, which is useful. That is -1, which is useful. And that is also 1, which is useful. Ones are nice when you're working in matrices. They are very useful. Now, you can see why I want 2 zeros here, because if I want to eliminate this, I got to add these 2 rows together. But if I have a number here, it's going to change this 0. So you've got to line up these 2 zeros first. Then I can start using just these bottom 2 rows to change this to a 0, and then we're basically done.
Say that it's like when we would eliminate x from 2 equations and...
Oh, yeah, that's good, that's good.
Say that.
Clearly, it's just like when we were eliminating x from 2 equations when we were solving for 3 planes, right? In the previous unit, when we were just doing lines and planes. It's exactly the same thing. I need to get rid of x, so I just have y and z, and then I can solve just those 2. Okay, so what I want to do, now I'm going to show you something else as well. Actually, let's take it slow. We got a few examples left. We can do it later. So I am going to do row 2 times 3. So 3 row 2. That's still 0. That's 3. That's -3. That's 3. Okay. We're almost done here. 2, 3, 1, 9. And now in this row, I'm going to add row 2 plus row 3. And I get 0, 0, -1, which was lucky, and -1. And that means we're done, because now we have a solution for z. Z, -z, I can come over here. Once we're done, we're going to stop. Like I said, there is a way that you can continue doing this with matrices, but that's not something that we're going to worry about right now. So once we're done, I can come over here, and I can say, therefore, -z equals -1. So z equals 1. And I can take this, and I can use it in the other equations that I have here. Are we good?
Yeah, but okay. Just let me do it. Let me do it. Okay. Will you edit this that I was doing this one all along?
Yeah,
later?
we
Okay.
can do that.
So now that we have z, we just go back substitution like we always have. Find an equation that has 2 variables, one of which is z, and work backwards from there. So if you look at row 2, we have 3y minus 3z equals 3, but now we know z is 1. And now we have y is 2. Right? So now again, find an equation with all 3. It doesn't even matter. You can go back to your matrix. You can go back to your original question. It doesn't really matter where you go, but find one of your 3 equations with all 3 unknowns. You know 2 of your 3 unknowns and work backwards from there. So I'm just going to use row 1 that we have now, which is 2x plus 3y plus z equals 9. But we now know that y is 2. This thing is so awful to work on.
Oh, it's fine.
It's fine. Look at how awful my writing. Okay. Plus, what was z? Z is 1 equals 9. Okay. So 2x equals 9 minus 6 minus 1. Okay. Now you should still conclude the way we've always concluded. So this means that the system actually has a solution. All three planes intersect in a single point. That point is 1, 2, 1. Okay? So therefore, the planes intersect at a point. I don't know how you write on this thing. Point. Say what the point is, and say the number of solutions. Awesome. And of course, like anything, you can always check your answers by going back up to the original equations and making sure that 1, 2, 1 actually makes the original set of equations true. All right, let's try another one. Question C. So again, obviously a system of 3 planes.
Zoom in a little bit. You're too far out.
I don't know how to do that. Like that?
Here, let me do it. Let me do it.
Oh my God.
Oh boy.
Okay.
There, like that. Okay, go, go.
All right. So we have a system of 3 equations, 3 unknowns. We're going to set up our augmented matrix. All you do is write the coefficients, a line to represent your equal sign, no, I missed a negative, and another one. Okay. So it looks like we could easily eliminate x here by just adding row 1 and row 2, okay? But we could also eliminate it by multiplying row 1 and subtracting row 3. Now, if you don't feel comfortable doing that much all in one question, then don't. But if you start to get really good at row reduction, you can do multiple eliminations all in the same matrix. So because this one's so super easy, I'm going to attempt that here. So I'm going to do row 1, I'm going to do nothing with. So I'm going to write it again. Row 1 plus row 2 will eliminate x because they both have the coefficient of 2. Well, one's 2 and one's negative 2, so we're going to add those together. So that'll make a 0, that'll make a 0, that'll make a 0, that'll make a 15. And I'm going to also attempt to do 2 times row 1 and subtract it from row 3 all in my head all at the same time. So I'm going to double row 1 and I'm going to subtract row 3. So if you double row 1, that would be now a 4. This would be 4. So 4 minus 4 would be 0. This would be negative 6 minus minus 6 would also be 0. Negative 2 minus minus 2 would also be 0. Okay? And 10 minus 10 would be 0. So what's the interpretation of this? We've got a 0 equals 15 and a 0 equals 0. Okay? That 0 equals 0 is telling us that row 1 and row 3 are just multiples of each other. Right? The entire equation is a multiple of the entire equation. So that means that plane 1 and plane 3 are coincident. They're actually the same plane. Right? Because by multiplying row 1 by a multiple and then subtracting it from row 3, I got a row of zeros. Right? So between plane 1 and plane 3, there are infinitely many solutions, but that's because those 2 planes are coincident. But look at row 2, which represents what we got when we worked with plane number 2. Right? We didn't get 0 equals 0, we got 0 equals 15. That means that plane 2 is parallel, but not coincident. Now, maybe matrices wasn't the best way to come to that conclusion. You could have done all the work we did in the previous unit. You could have looked at N1 for this, and N1 for the, or N2 for this, and N3 for this, and compared the N's like we always have, and come to this same conclusion with maybe less work. Right? But if you don't notice that, or if the question says solve by matrices, and you have to do it by matrices, we have to be able to interpret what does it mean if we get 0 equals 15? What does it mean if we get 0 equals 0? And we have to look at all 3 planes. We can't just look at 2 of them. Okay? So we've solved the system. Okay? 2 of the planes are coincident. 1 of the planes is parallel and distinct. So overall, this system has no solution. Okay, let's look at another one. Now what? Where is it?
I don't know, you just have to find it. There.
I can't find it. Okay. What is going on in this one? All right. So guys, you can see that there's a variable missing already. And as we talked about earlier in the video, it's a good idea to have your zeros at the bottom. So you may want to make this row 3 right from the beginning, right? Or at least row 2. So we have a 1, 1, 2, our equal sign, and 4. We have a 0, 5, 6, and 4. 2, -3, -2, and 4. Okay. So part of the work has been done for us because we have a 0 right here. Okay. But we still need to make this into a 0. How to make that go away again?
Holding the little
Hold the
button.
button. All right.
But you're going to erase the whole thing now.
The whole thing? What are you talking about? Just that? I can't erase
Push
just
it
that?
in. Here, let me do it. There you go. Okay.
That was cool. Okay, so, you're going to fix that later?
Yeah, I'll fix it.
Okay.
Don't worry, don't worry.
All right, so we need this to be a 0, which means that we need this to be a 2, so that we can subtract the rows, or a -2, so we can add the rows, whatever you are more comfortable with. So I'm going to do row 1 times 2. So that'll become a 2, that'll become a 2, that'll become a 4, that'll become an 8. This one already conveniently has the 0 where we need it, so I'm not going to do anything to row 2. Okay? And row 3 I'm just going to rewrite so that we have it all lined up for subtraction in the next matrix. Okay, so now when we subtract row 1 and row 3, we end up with a 0 where we need it. So row 1, we do nothing. Row 2 has the 0 where we want it, so we do nothing. But now, when we subtract row 1 minus row 3, 2 minus 2 will be 0, 2 minus -3 will be 5, 4 minus -2 will be 6, and 8 minus 4 will be 4. Good? Okay. Now, the coefficients are already correct in order for us to just do row 2 minus row 3. Okay? We're not going to do anything to row 1. We're not going to do anything to row 2. And we're going to subtract row 2 minus row 3. Okay? And see what happens. So 0 minus 0 is going to be 0. 5 minus 5 is going to be 0. 6 minus 6 is going to be 0. 4 minus 4 is going to be 0. And so now what we have here, guys, is what we've had in the past. That's 0z. That's 0. Okay. Well, 0z equals 0 means that we have infinitely many solutions. Is that okay? Infinitely many solutions. Right, but along a line. Okay? So just like we've done in the past, you now let z equal t and just keep back substituting. If z equals t, now sub that into row 2. So you have 5y plus 6z equals 4, but z is t, so 5y plus 6t equals 4. So y equals 4 minus 6t over 5. So that's your parametric equation for y. Okay? And then back substitute that into equation 1 or to get what x is in terms of the parametric equations. Now, you can use any version of row 1 that you want. I'm going to use this original one here, not the one where I multiplied by 2, but of course you would get the same answer if you use the one where you multiplied by 2. So the original row 1 was x plus y plus 2z equals 4. Right? But y is now 4 minus 6t over 5, and z is t. Okay, now we want to solve this for x, or simplify it for x, and then our final answer will be a line. So the three planes must intersect in a line, so this must be case 7. Negative. Okay. Now, don't forget to write a conclusion. So therefore, the three planes intersect in a line. Define the line using your parametric equations. Write it out as a vector. That's a t. So this was 16/5. Y was 4/5. Can't read this at all. This was 0. Our t coefficients were, thank you. Our t coefficient for x was -4/5. Our t coefficient for y was -6/5. And our t coefficient for z was 1. Now, a lot of times in the solution, they'll clear the fractions, so they'll do a scalar multiple of that. So you might see the answer like you have in the previous unit, where they do a scalar multiple of the direction vector. So p naught won't change. But you might see this written as -4, -6, 5. So the whole thing's been multiplied through by 5. Okay? And number of solutions, infinitely many. Okay. Are we done? Look at how messy that is. Where's the other question?
That's it.
That's it.
Wrap it up now.
Okay. All right, guys. So remember, as you do your row work, that you write it beside the row. Keep that in mind. Remember to still back substitute to get answers. And remember, just like before, write a conclusion. Describe the geometric interpretation and the number of solutions. The end.
That was awesome.
No, it was not.
Good lesson. Yeah. I thought it was really good.
Okay, I guess, but you're going to edit all that stuff.
Yeah.
It'll be
I'll
cleaner.
edit all that, yeah.
I don't know, isn't that answer even right for that one?
Yeah, remember we wanted to change that one,
Oh,
so it ended it
yeah,
as a line,
line.
right? We talked about that.
We did talk about that.
I forgot to stop recording. Whoops. I'll fix this. Don't worry.